fabrication. Some other plants that receive those already formed parts. So then it'll go to welding for adding slightly more material. Then it'll go to paint where it is washed off, it is prepped for paint, and then it is painted and cured. And then it is assembled and finally shipped. And all of these plants follow a very similar pattern to this.
And talking about the incentives for change, a lot of environmental goals for Great Plains has been driven by Kubota. Kubota is the corporation that acquired Great Plains in 2016. And one of the important things there is reduction in carbon emissions by 9% per unit produced by 2025. A reduction in carbon emissions by 50% across the company by 2030. And they want to be carbon neutral by 2050. 2050.
So some of our key projects were forming energy maps, which Aabhash will talk about in a little bit. We did a chip cure oven heat retention project, trying to reduce energy losses through an oven. A wash line conservation project, and we looked at fans, lights, and compressor air leaks as well, and a couple of plants. So.
All right. Well, so the first fun project we did was energy mapping. So what even is an energy map? It's a visual representation of energy consumption across a plant on the basis of area of manufacturing. So you can do this in tons of different ways. You can make a map and then put colors there, gradient. You can have a bar graph, you can have a line graph, but the one that we chose for Great Plains manufacturing this summer was a pie chart. Couple of them. And so what we do is we locate with the energy maps, we locate areas of high consumption and focus P2 pollution prevention initiatives on those areas preferentially for the greatest savings. This is a theory for Kubota's energy efficiency as well. They want to look at places where they have the highest consumption and get projects at those areas. So as mentioned before, we did our energy maps for the Kip and Abilene plants. Our methodology for this project was first locating, so left to right, first locating the device itself, see what devices are there, what's taking energy. Second is looking or finding and then collecting data from the nameplate, the most important data points that was necessary for the energy map were voltage, amperage, and phase, sometimes horsepower. And in some devices that we could not access or we could not get the nameplates for, we had to use other forms of data collection, which includes using an M-clamp like that, or just looking at the internet, which always seems to work. And the fourth picture that you see there is the spreadsheet with which we created those energy maps. I apologize for the very small font there, but you have the area of where we found those devices, the name of the devices, the quantity, the amps, the volts, and all that stuff, all to calculate the energy the demand first and then consumption. And here's the results. On your left, you can see the Kip energy map. On your right, you'll see the Abilene energy map. Some things to know: paint in both the plants consume the most energy, which is understandable as it consists of the cure ovens, the dry ovens, the wash line, and the paint line itself. Other usual suspects of high energy consumption includes welding. You have fabrication on Abilene and compressor at Kip, which is interesting and we'll get into later. So savings and benefits from this project. So what do we have? Well, none, sort of. Oh, sort of, because all we did was find which area is consuming the most energy. We didn't really do anything per se. But as mentioned before, the main goal, the main focus of this project was to find areas of high consumption and then do projects on those areas so that we can get the highest returns.
One of my main projects this year was looking at the cure oven at the kit plant and trying to find ways that we can keep the heat that's escaping the oven inside of it. So if anyone who's been, I mean, Ben and Kelly know, anyone who's been around that oven knows that it's like being 5 inches from the sun. It is so hot near and especially in front of the face of the oven. So I saw that as definitely a huge source of waste heat and wanted to look at ways, first of all, how is heat escaping the oven? And second of all, how can we keep it in? So I tried using some of the basic thermodynamics that I learned in school to create an oven of the cure, a model of the cure oven. So go ahead. So heat's escaping this oven. If you can see my drawing in the top right, in 3 different ways. There is heat traveling through the floor via conduction from the hot oven floor to the foundation of the building. And that ended up being not very significant, 3.1 kilowatts. It's probably not worth addressing. Heat is escaping via convection by both free convection pulling heat off of the oven walls as it seeps out. And there's also an exchange of air between the inside and outside. So the oven is pulling in cold air, ejecting hot air, and all of that energy is just being used to keep nature warm. And it doesn't need any help with that, especially right now. So then the final way that heat can escape this oven is by radiation. There are a number of heating elements within the oven that that sends IR light to help heat metal parts up. So the convection and radiation ended up being the largest sources of issues with this oven. So next slide. This is how we thought to address it. First, we were going to put a heat curtain up to address the radiation. This is a physical curtain that blocks the light from escaping the oven. And what it would do is it would prevent up to 50% of this radiation from escaping. It would keep the air within the oven by becoming hot itself, and it would also reflect these IR rays back onto the metal parts. And then we've also got a couple of air seals installed in the oven already, but they're not running because the plant is, there's enough dust and grime in the area that it would actually kick it up onto the freshly painted parts. But turning these on could save up to 90% of the air energy, or the hot air energy that is escaping the oven. So with these two things, if you go next slide, we're looking at potentially $10,000 a year, and that is a pretty low ball. A lot of these were estimations made, so I tried to be as conservative as possible. But a simple payback of 70 days and preventing up to 32 megawatt hours and 44 metric tons of CO2 every single year by installing a $600 curtain and turning something that's already installed on. Now, there would need to be some cleaning regimens put in place to run those air curtains, but it seems to be a pretty simple fix, not a very complicated issue. And yeah, decent benefits.
Next online in projects is the KIP wash line conservation project. So first thing I'd like to talk about before we even get into the project is the layout of the wash line. First of all, of course, the wash line is part of the paint line, and if you remember, it's taking 35% of, it's consuming 35% of the energy at KIP. So the layout of the wash line, you have your first stage washer, which uses Gardabone 9840 chemical. You have a small rinse station, which is just a frame, which you can see right in there. That's the rinse station. And then you have a couple of dry blowers right around here, which is right in front of the dry oven. And you also have a boiler that's heating hot air, hot water into a heat exchanger that then heats the Gardabone and the water at the stage 1 washer. And so our locations of interest was the rinse station itself, that thing, and the boiler pipeline. So in terms of the rinse station project, the problem was, as you can see there, the line is running, but there's nothing on the line. There's no object on the line, but you can see that the water's still running. So the problem with that is you have so the water is being recycled, but we know for a fact that it's not being captured all throughout, because every day they're adding 250 gallons of water. So you're losing water, of course, but you're also wasting energy in terms of electricity, because you're running the pump not 24/7, but all the time that the paint line is run. And you also have the dry blowers, which are running all throughout, consuming electricity. So what's the solution? The solution is getting a set of sensors that will sense if there's nothing on the line, if there's no object on the line, and then stop both the dry blowers and the sump pump that's running the water. And in terms of the boiler pipeline project, the problem is that if you can see here, there's insulation from the boiler line to somewhere around the middle, but it just stops getting insulated, and no one knows why it's not insulated. I asked everyone from newcomers to oldcomers. They just, I don't know, they just didn't insulate it. So the solution is just insulate it. Pretty simple. So that here you see is an inch of steel wool insulation, and the same thing can be done for the entire length, which was 32 feet. And just to show that it works, the temperature at the of the pipeline when it's insulated is 95 Fahrenheit, and the pipe in itself when it's not insulated is 171. The thermostat is set at 185, and the temperature of Gardabone has to be between 90 to 120, which is interesting. So the savings and benefits from this project, we do have something, unlike the energy map. We're looking at around 28,000 gallons of water being saved, 61 kilowatt hours of electricity from the sump pump and the dry blowers, and 24,000 MBTUs heat, and which all adds up to around 61 metric tons of CO2 and $9,868.
Our next project, this was just kind of done out of curiosity in one afternoon. With a conversation with the maintenance people at Abilene, it was found out that that the lights and fans on the floor are run basically 24/7, and the plant does not run 24/7. So I just went through a schedule of what areas of the plant run, when are lights turned on, when are they turned off, they're never turned off, and found that literally if we just retrain the night crew, now this is super ideal because it's hard to get people to care about this, but if you just turn lights off and turn fans off, it is almost $28,000 a year and 300 metric tons of CO2 a year that are just being wasted in lights and fans. So we didn't have time to look at occupancy sensors or time sensors. A time switch would be perfect for this situation though. It would cost practically nothing in the grand scheme of things as far as savings go. So, oh, I guess I'm still going. So we also went around. Actually, do you want to explain compressed air leaks?
Yeah, sure. So compressed air leaks is also one of the projects we just wanted to do at the end. And so Everything's knew that there are significant air leaks in their plants, but they never really had numbers to justify fixing them, because fixing them takes a stopping of 30 minutes of work, which is pretty significant in the long term. So the goal of the compressed air leaks project was to just survey different plants and then get leaks and then get numbers to the leaks so that the corporate could understand that these are significant and worth looking after.
Yeah, so we went through, we found that the average leak was costing about $575, almost 6,000 kilowatt hours per year, and almost 6 metric tons of CO2 every year. At a very, very, very low ball for 300 leaks across the entire company, that's $172,000, 1,700 metric tons of CO2. It is ridiculous. Compressed air is a huge waste. So another thing that we've been doing is looking at how we can save energy by reducing the working pressure of compressors. We didn't have really the resources to get decent data for energy in, energy out, stuff like that. So a pretty rough rule of thumb in industry is you get a 1% energy reduction for 2 PSI reduced in an air compressor. We went ahead and used that, and then another very rough approximation for the average Great Plains compressor. some of the stats that are listed here. We found that reducing 1 pound per square inch across all compressors in the company would save $13,000, and that's $132,000 if you reduce 10 psi. Our kit plant that we were talking about, the small one, has a lot of compressed air leaks and relies somewhat heavily on compressed air for some of the processes. And they were able to reduce by 10 psi, no problem. And our price saving about $5,000 a year, 35 metric tons of CO2. So it's not unfeasible, and it would take pretty much just an iterative process of lowering the pressure, seeing if it's a problem, lowering it more, see if it's a problem, stuff like that.
So in terms of challenges, the first challenge we got was in terms of energy mapping. We just, we had to get through equipment runtime just to be as accurate as possible, and we had to ask around, and we didn't always get the best answers or the most accurate answers. We also had problems with getting the nameplates early on because we didn't know where to see if we did not have a nameplate. Another challenge we had was in terms of the paint line object gap. I was working, before I even went to the plant, I was working on my calculation of the first stage washer. So I was putting the chemical and the big washer, big electricity savings. I was getting all that. And then when I went to the kit and saw the actual things going on there, I realized that the first stage washer did not even need a sensor because of how good its efficiently is actually running.
Some of our recommendations, and especially future project recommendations for the next interns, is finding as many equipments or devices we can switch to battery power instead of air power, because air power is at best, 1/7 the efficiency of electricity. So trying to replace or downgrade compressors, maybe relocating them closer to where they're being used, and installing variable frequency drives in the compressors that help to increase the efficiency.
Makeup air units consume a lot of energy, and a lot of spots we found at Great Plains, they are bigger than they actually need to be, and we feel like they could be downsized or turned off for an hour or two when no one's inside. There's a lot of things that could be researched, we feel like, and that's why we kept it there. The last one is heat capture. A lot of Cure oven exhausts and sorts have hot air and heat just going out, being wasted, and if you're not saving it, you're wasting it. So there could be something that could be done with heat capture, we feel like, which is something that the future intern could work on. And that's it. Any questions, comments?
So for the peak line with the installing a sensor for turning the water and the blowers on and off, how long do they take to power back up after they've been turned off?
Yes, that's an excellent question. So it's always a problem when you think of turning off and on, off and on. With the sump pump in itself, it's a smaller motor, so it's not going to be a big problem. So it's like almost instantaneous. Well, with the big blowers, these are bigger motors, but they're connected to VFD, which means that you can slow it down and turn it up in pretty much I wouldn't say instantaneously, but in a rate that does not affect production is what we've found out. Thank you. Nancy?
I have a question, yeah. And so, excuse my ignorance, but when it comes to the compressed air, and you said just reducing the pressure, I actually had not heard that stat about, reducing by 1, Yeah. So I don't know if you can flip back to that slide even, because I'm not going to say it right. Okay, 1% energy reduction per 2 PSI reduce. So literally, are we talking about a dial? How do you reduce it?
So a lot of compressors, at least all the ones that we found, you set a pressure that it either fills a tank to, or it's mostly just a target. And there are pressure sensors that it makes the compressor work as hard as it needs to. So if you bring that goal down, if you bring the bar lower, you don't have to jump stop, basically. Right. Yeah. So Yeah,
So
pretty
it's
much.
just programmed in.
Yeah, it's a matter of clicking a few buttons. Yeah.
So most of our compressors that we found were set to about 125 PSI. I mean, I think the lowest maybe 119 or something of that nature.
Kip's down to 100 now, right? Yeah. And we found that most air tools require between 70 and 90 for proper function. Obviously, there's going to be pressure drop across lines and leaks are going to be a problem, but yeah, you can see if that's a problem in about 5 minutes, probably.
That's great, because that's another type of new suggestion that I haven't heard before, and I've been working in the program since 2006.
Yeah.
So we're always looking for those new kinds of ideas.
Yeah.
So thank you, because a lot of different people can use that. And that's a big part of our job is what we call transferability of knowledge.
Right. I will say, everywhere I read that, I read it in a lot of places, but they all said, this will give you an idea of the scale. You have to do a more proper analysis if you want to get actual numbers. So just as a comment. Yeah. Yes.
Great presentation.
Thank you.
My question is Jay. You talked about installation of the air curtain, right? Thermal curtain.
Yes.
So that would for infrared oven or convention oven.
So it's and there's a,
And if it's the convention oven, then there's the conveyor belt, right? That goes through it.
or are you convection versus IR?
No, for the convection oven, if you're thinking about adding the curtain there, it has a conveyor belt going through it.
Right. That would
How are you?
disrupt, I mean, that would make it work not as well, obviously, because it's disrupting airflow, but the space between parts is between, I would say between 5 and 10 feet probably between each part of the kit. So, and the line moves between 5 and 8 feet per minute. So there's a lot of time where that space is completely open. So it would mostly help during that time, I would bet. And I think on the whole, I haven't done any calculations. If you just ask my gut, I would say that it probably helps overall.
Yeah. Surplus project. You do.
Yeah.
And to help him out a little bit with that, it's a slatted curtain, so that's
Okay.
free flow with the parts coming out
Okay,
and then
okay.
things like that, but would contain the heat for the most part on the back end.
Yeah.
Well,
so
it's-
the back end, one end, and
Or is the air curtain that we were talking about, the air seals?
You were talking about the curtain.
Yeah.
Oh, okay.
Yeah.
Never mind.
Okay.
I was thinking about the physical curtain.
Yeah.
No.
I have a comment on the chat. Keely said, really great heat transfer diagrams and explanation.
Thank you, Keely.
Yeah, I had a question on the Krehbiel. How, because you were able to kind of estimate how much energy was being lost, through like the convection and all that. How did you end up modeling that or coming up with those numbers?
So it was admittedly very rough. I could talk about the radiation thing for hours. I spent probably 20 hours in VBA coding, like using view factor equations, stuff like that, it was a nightmare and a half to do that. But the convection, it was pretty simple, like mass flow rate, heat capacity, temperature difference, and it doesn't take into account the temperature profile or flow pattern or anything like that. So it's very rough, but it was more, the point was to give an idea of the scale of the problem more than anything. So and I think that equation does a decent job showing that. But yeah.
Oh, sure. Do we have time?
yeah. we do have.
So one other question, same question I think I had for Cooper, right, was, how do you think, looking at the energy map and the potential uses and savings, how impactful would some of these projects be in helping Great Plains meet their goal for reductions of GHGs?
I'll say the same thing that I was thinking when you asked that question. Yeah, I should have done that. Should have done that. We hope it's gonna be great, but we didn't actually quantify that. Jacob?
Real simple, short question. On the energy map, you had a pie chart of different percentages of where energy was going. Could you go back to that, is there anything that shows the absolute scale of actual energy that's being used so that you can essentially say that, hey, of this total energy, 35% is being used, given what is the actual energy from the main? What is the scale that being used to?
Yes, we do have it in our spreadsheet, not here. But you'll find it there in the report.
What is the coloring on the spreadsheet?
So now we just wanted to be, assembly is the same color. Thank you, Kelly. Welding is the same color. We didn't really think much about coloring.
On the spreadsheet itself.
Oh, okay. My bad.
Yeah.
So this is, green is less energy consuming, yellow is medium, red is very high.
And so we could find it faster.
Yeah.
And we forgot to take it out.